So that last calculation was if you're just given an amount of one reactant and you're asked how much one product can be produced, just based only on that. Well, it doesn't even have to be reactants or products. If you're given one mass and are asked for one mass, okay, you just go grams to moles to moles to grams. It can be really anywhere in the calculation. Where you have to do a little more work is if you're given amounts of more than one reactant. We have to find which is the limiting reactant in that case. Okay? So we need to answer the question, which reactant is consumed first? Because of the way chemical reactions work, they work as just sort of assembling pieces together, and as soon as any one reactant runs out, then the reaction stops. So the reactant that runs out ends up being the one that determines how much product we can be formed. And everything else is in excess. Everything else just sits there. Okay? So what we're going to do is calculate the moles of a single product that each reactant will make. Okay? Many times you'll be asked about a product, so it's helpful to do the calculations about the product you're asked for. Sometimes you're not asked about a product. Sometimes you're just asked which reactant will be used up. So you just pick one of the products, okay, and do the calculations for that. Okay? But it's important that you do this in terms of how much of a certain product can be formed. Okay? That's probably the simplest way to look at it. The reactant that makes fewer product moles is the limiting reactant. Okay? And that's how many product moles can be formed. So let's start with a unbalanced equation right here. I guess it is balanced. I put the 2 in front of HCl there. But you should always double check, okay, to make sure that a chemical equation is balanced. And if you're just given a word description of something, you'll have to write and balance it on your own. But it never hurts to double check. Okay? So let's do just a real simple one with moles. If 0.30 moles of zinc react with 0.52 moles of HCl, how many moles of H2 can be formed? But again, we're given 2 reactants. Right? Zinc and HCl are both reactants. And anytime you're given information about multiple reactants, you have to figure out which is the limiting reactant. So we need to set up 2 calculations. One starting with moles of zinc, one starting with moles of HCl. Okay. And this is asking about moles of H2. So moles of zinc, moles of H2. What is the mole ratio for zinc and H2? Yeah. If you want, you could put 1s in the blanks if that's helpful for you. Nothing wrong with that. So that one's easy. 0.30 moles of H2 will be formed. But then we got to do HCl. Moles HCl, moles H2. Okay? Don't forget, you're always ending in the unit of whatever substance it's asking you about. Okay? A lot of people sort of get confused by converting one thing into the other reactant, and you sort of start switching things around, and it becomes very confusing. It's totally the simplest to just convert everything into the same product, so you're ending the same place in each of these calculations. 1 mole of H2. How many moles of HCl down on the bottom then? Yeah. That's okay. So 0.26. And a lot of students answering this kind of question like that would just leave it like that and go on. But that hasn't answered the question, right? The question is how many moles of H2 can be formed? So what is the actual answer to this problem? Yeah, 0.26 is how many moles of H2 can be formed. Let's even write that. And what does that 0.30 mean in this problem? Can we produce 0.30 moles of H2? Not in this problem. Okay? Not unless we got more HCl. Okay? If we had unlimited HCl, the zinc would run out when we got to 0.30, but not in this problem. Okay? So let's write cannot be produced here. I think it's a great habit to get into. When you identify a limiting reactant, put a box around the answer that you actually can produce. Cross out the other one, because that is meaningless to us, okay? At this point anyway, in this problem. Okay? That will prevent you from trying to do wacky things with that 0.30 answer, okay? And so on. All right. So it may be helpful for us at some point to calculate the amount of leftover reactant, because which reactant here is going to be left over? The zinc is going to be left over. Let's call that one excess. Let's call the HCl the limiting reactant. Does any of this sound familiar to you, reacting with zinc and HCl when some zinc is left over? And does that ring any bells for anybody? Let's calculate the amount of leftover reactant. Okay, let's first calculate the amount of excess reactant that was actually used. Okay, so what I'm going to do, right, because here's the excess reactant, to figure out how much was actually used, I'm going to take my answer, okay, from before, and I'm going to start with that. Okay, let's start with the 0.26 moles of H2, which can be produced. Product amount that can be produced. And let's go backwards into the zinc. So H2 and zinc. Moles of H2, moles of zinc. Go back up here, double check the coefficients. 1 mole of H2 for every 1 mole of zinc, so we're good there. So 0.26 moles of zinc, okay, will react. Okay. We're told in this problem that we started with 0.30 moles of zinc. So how do I figure out how much zinc will be left over in excess? Yeah, you just subtract. Okay. Let's take our 0.30 moles of zinc. Let's say added to the reaction minus 0.26 moles of zinc, okay, that reacted, and we got 0.04 that remain left over. I'm going to use lots of words to describe this because you see this described many ways. Left over, or we could say in excess. Let's say unreacted. Okay. So be prepared to look for many different ways that this could be described. Okay. I know if you get used to seeing it all from one source, you can be thrown off when the wording is different. So make sure that you're able to interpret that in any way. But the key, anytime the question is asking how much is left over or how much remains unreacted or anything like that, is to first calculate how much product you actually can form, okay? And then from that, go back to calculate how much reactant, how much of the other reactant would actually get used up to make that. Okay? So that's what's happening here. We calculated 0.26 moles of H2 could be formed. Okay? From that, we go back and figure out, just using its mole ratio, how many moles of that excess reactant would actually get used up. Okay? So in this case, the 0.26 moles of zinc would react. We subtract that from the moles of zinc that we actually started with. Okay? So this was an entirely mole-based calculation right here. That can totally happen. Okay? But this is the core of this type of calculation. Anytime we have grams, that's just sort of an additional layer on the outside of that. But at the core of all these calculations are these mole ratios that get us from one thing to another. We can put anything we want to in grams. We just have to convert from grams into moles. And then when we've got an answer in moles, we've got to get that back into grams. Okay? So if your question is grams, grams are kind of the first and last thing that you have, but it's kind of moles in the middle of it. So let's give a question like this a try with grams. Here's a balanced chemical equation. Sort of a unique one because we're using S8 in this one. That's a specific form of sulfur. I think we talked about that a while ago, where it forms those 8-membered rings of sulfur atoms, but that gets accounted for in the balancing. Sort of like that. So 7.36 grams of zinc react with 6.45 grams of S8. How many grams of zinc sulfide can be produced, and what mass of reactant remains? So we're going to start out two parallel calculations. And then we're going to do 6.45 grams of. So what ends up being the most useful is calculating moles first of the product in question. So start with that. That's where we can determine the limiting reactant. You could actually go all the way to grams here, but then you're actually wasting a little bit of time. This is actually most efficient to go to moles right at this point. So go to moles, make a decision based on the moles of your two products. Then you could calculate grams of products, and then you could do like we did on the last page with leftover. So don't forget, though, when you're starting in grams, the very first thing you have to do with those grams is convert them into what? Yeah. Very first step, always when you're starting with grams, is to convert into moles. When you've got any kind of balanced equation going on here, convert your grams into moles first, then use a mole ratio. Also, it's important you know the difference between the coefficient and the equation here. Okay? This 8 coefficient, that gets used in a mole ratio, but this one right here, that gets used in the molar mass. So when you're calculating a molar mass of S8, that's the actual formula there. When you're doing the mass of zinc, it's going to be just the mass of zinc. It all ends up equaling each other out anyway, but what you want to make really sure you don't do is use it twice somewhere, or use it never. When you start getting mole numbers, compare those with your neighbors. make sure you use the coefficients here. So yeah, and that's 8, 8. That's pretty much the same thing, but only one of those is going to be 8. So. Give yourself at least a couple extra sig figs over in these moles because you're not done with those. Right? And don't use rounded values in your subsequent calculations. So your point 11257 for that first one. So just 3 sig figs, so let's underline that 2 there, but let's give ourselves a couple extras. All right. Did you put 256.56 down here on the bottom? Because you got to do 2 S's for that formula, because it's S8. That's what that formula is. But that's per 1 mole, S8. The places I see students get confused, sometimes 65.38 grams of zinc, sometimes someone might want to write 8 grams of zinc in there, but molar mass is always per 1 mole. That's sort of the definition of molar mass. These coefficients over here, they only get used in the mole ratios. So I would still recommend putting 8 to 8 for that one. You don't have to even enter it in your calculator because it's 1 to 1, but I would still put 8 to 8 there so you're not forgetting about it. But that's especially important over here because the mole ratio is different down in this one, right? Eight moles ZNS per what down here? Per 1. So make sure that that's correct. What'd you get for that one? Yeah. So I'm not even going to write down any more digits because I know that one's not our answer, right? So if I were you, I would get in the habit of just crossing out the larger value there. That doesn't really mean anything to us. So what is the limiting reactant here? That's a good question. Yeah, the limiting reactant is over here. Okay, that's not the limiting reactant. This is the limiting reactant. Okay. This is how much product can be formed. That's the reactant that will run out. What would we call S8 then? What's the opposite of the limiting reactant? Excess. Let's call that one excess. All right. So what do we have to do to answer our first question? How many grams of zinc sulfide can be produced? Put it into grams, right? We calculated how many moles. Let's take those moles, 0.11257, and that's why it's important to give yourself a couple of extra sig figs. 1 mole zinc sulfide, 97.45, I think, is what the molar mass is. Did anybody else add that up? Is that right? Okay. Thank you. So how many grams of that product can be produced? Let's call it 11.0. Okay, so there's one answer. Can be produced. Okay. Then what? What back to moles? This? Well, I've got that already right over here. Subtract it from the what? Well, from something. 97.45? Where was that? Molar mass? All right, let's look back. What we did next over here, okay, we had moles of a product that can be formed. To do the excess, we took those moles of product, we calculated how many moles of reactant would actually react. Okay? So let's do that. Let's take the 0.11257 moles. Okay. And then into moles of what? Yeah. Moles S8. Okay. Let's double check our coefficients. 8 moles of ZNS, 1 mole of S8. Because that was the excess reactant. What we want to find out is how much of the excess reactant actually got used up. Okay? So we're going backwards. We're taking essentially this value over here and working backwards to S8. Yep, 0.11257 divided by 8. Let's do one more sig fig, 14071. Yep, I say were used. Okay. So then what? Yep. You could actually go two ways. It's okay to subtract grams, or it's okay to subtract moles. Okay? Pretty much whatever's convenient to you. If I subtracted moles, I'd have to get the answer back into grams again. So let's actually, tell you what, if we're just doing straight in grams, let's just go straight to grams from here. Let's say 1 mole S8. Let's say 256.56 grams. I think this does it with the fewest. Sort of the fewest steps there, 3.6. 3.6101 or something like that. Yep. I think that's probably the most convenient way to do it because we're given grams of a reactant. So if I just add on the molar mass right there, we can figure out how many grams of that reactant were actually used. And then because the question was what mass of reactant remains, now what do? Yeah, now we subtract. We do what minus what? Yep. I'm running out of room here. Here, I'm going to write it right up here. 6.45 added. And I can do 6.45 minus answer in my calculator. If you have a two-line calculator or a graphing calculator, it'll say answer, usually down in the lower right as up above one of the keys. It might be above enter or above the negative or something like that. Get used to using that. Okay? It will save you from retyping things in. There's also a way to do that on a one-line calculator, but you have to plan ahead a little bit. You have to save something to the memory, and that works. Or you could just give yourself extra sig figs and type it in. So what'd you get? 2.8. So we subtracted. You're limited by decimal places of the fewest, whatever had the fewest decimal places, right? So 2.84. Okay. So that's a calculation you'll have to practice a little bit. The part that's a little unnatural is probably right here. Okay. I think we've all probably done the calculation before where you calculate how much product you can make. Okay? But then if we're ever asking about what's left over, you got to start with those product moles again, okay? Convert back into the excess reactant. Okay? The excess reactant. And if the question is asking moles, you can just subtract moles. That's fine. If the question is asking grams, okay, it probably works best to calculate grams of that excess reactant, okay, that we used. So let's just make a little flow chart here. Moles of each product to choose the limiting reactant. Okay. Product moles to grams for product mass. Here we go product mole to excess reactant moles, then to grams. Then we did grams added minus grams reacted. There we go. That's about the basics of what happened there. So that's one that you'll have to practice. If I were you, try to do something like that on a blank sheet of paper. Maybe just start with this one. So you got a nice place to go off of. Maybe on a note card or on a page of a page that you use while you're practicing or something. Maybe write out the steps to these kinds of things. That's also very helpful in all these combustion analysis problems, okay, the ones we talked about last time. As you're practicing those kind of things, start making out little flow charts, make out lists of things to do, so that you can help yourself with that. Let's just do one more quick thing before we go, just on the bottom of this page. Theoretical yield and actual yield. The theoretical yield is a calculated product mass from a stoichiometry calculation. It is the maximum amount of product possible. Let's just say that. In the real world, we will never get every last molecule of product out of the flask, scraped out of there and into the balance or something. You'll always lose something. Reactions don't go to completion either a lot of times. So in the real world, we very rarely get even even close to the theoretical yield. So actual yield is a measured product mass. So if you actually did a reaction, measured the mass of a product, okay, that's actual yield. So let's say up above was 10.2 grams from the problem above. Okay. The percent yield will be the actual divided by theoretical yield. So 10.2 grams actual. The theoretical yield that we calculated was right up here. Let's call this theoretical yield. Okay. Anytime we calculate grams of a product in a calculation like this, that's theoretical. So that was 11.0. So you're just calculating a percentage like you would a test score or something like that, right? How much you actually got divided by how much you could possibly get. This one was pretty good. This was 92.7%. If any of you go on to take organic chemistry, second-year chemistry classes, every time you do a lab, you will calculate a theoretical yield. You will divide your actual yield into that, and sometimes you're graded on what your percent yield is, how close you get to the theoretical 100%. So, all right.